Alright, thanks for coming to watch this supplement video to lesson 8.1. If you already watched the original video, you might be a little bit confused, right? The concepts here are pretty strange and tough. So I thought I'd do this with you first before doing the actual supplement material. I know this page is not in your notes. I'm sorry I didn't photocopy it in there. But hopefully you can just maybe follow along and try to understand this concept. Okay? I'm going to ask you to look at this alternating series. How do we know this is alternating, by the way? Yes, the negative 1 to the power. And I'm hoping that you can write out the first 6 terms for me. So plug in 1, plug in 2, plug in 3, 4, 5, and 6. Okay? You'll notice that when I plug in 1, it's negative 1 to the power 2, so it's positive. So the first term should be just 1 over 1. The next term will be negative n, so negative 1 over 2. Plus 1 over 3 minus 1 over 4 plus 1 over 5. I hope you can see why this is alternating. Okay. Now here's what I like to do. I like to calculate what I call the partial sum, meaning just take the first n terms and let's see how the sums are calculated, and let's also visualize it. So s sub 1 means just take the sum of the first term. Well, that's just 1. So that's me starting at 0 and woo, going all the way to 1. Yeah. S sub 2 would be the first 2 terms, so that would be just 1 minus a half. So notice what I had was I went to 1, there's my first term, right? But then I had to subtract a half, so now I'm actually at 0.5. Okay, 0.5, right? How about S sub 3, so the first 3 terms? That'd be 1 minus a half plus a third, which of course, if you look at fractions, that's 5/6. It's a decimal, that's about 0.833. So 0 to 1, 1 to a half, and then adding 1/3, now I'm right about there, 0.833. Okay? Get the idea? So you try the next ones yourself. Okay? 4, 5, and 6. Okay? Go for it, please. I think that's 7/12, which is 0.583. Oops, too far. Getting excited. Back to a half. Adding a third. Minusing a quarter. Okay. Hopefully you can see what happens with the next one. By the way, that's 47 over 60. That's approximately 0.783. And for S sub 6, I'll just tell you the answer. It's 37 over 60. That's approximately 0.616. So do it, and then do it. There we go. Now, hope you get the idea. Each successive term in this sequence of a partial sum is actually between the 2 previous terms in the sequence. You see how it goes back and forth, back and forth, back and forth? So hopefully you can then understand that the actual sum S must be between any 2 successive terms as well. So looking at the last thing here, I know that the actual sum will be somewhere in between these 2 successive terms. I know it won't be outside here because it can't, because it's going to be less and less and less and less and less. Okay? So really what I mean by that is, look, if I looked at the row up here, you could see that the sum of the first 4 terms was actually less than what the actual sum would be, but it would also be less than S sub 5. Okay, right? S sub 5 is here, S sub 4 is there. We know the actual sum must be in between. If I were to look at S sub 6, though, you would see that, yeah, S sub 6 is actually less than the actual sum, which is also less than s sub 5, right? Here's s sub 5, here's s sub 6, and yes, the actual sum must be somewhere in the middle. So in general, we can kind of say that the actual sum must be, yeah, between successive sums. Right. Okay. So I'd like us to look at that previous example again. And now if I actually plotted the partial sums on a two-dimensional grid with the sum being on the x-axis and the number of terms on the x-axis, the sum on the y-axis, you'll see what happens here in the graph. So it goes from 1, then all the way down to 0.5, then you see how they get closer and closer together, so the gap is getting closer and closer. Well, the actual sum must be somewhere here in between. Okay? So, to generalize this, I want you to consider this alternating series now of a whole bunch of terms, where, of course, all the terms are positive. Okay? Looking at the actual values, but of course they are alternating because every second term has a negative sign in front. Okay, and all the conditions of the alternating series test are met. Okay, and if you don't remember them, go back to your lesson 7.6 notes. And now what I like to do is actually visualize the relationship between the value, okay, the value is the term, the nth term, the sum of the nth term, and the sum of the next terms. Okay, the partial sum of the next terms, using two different scenarios. Okay, so in this case, n is an even integer. So like the fourth sum or the sixth sum, that's where you'll see that the sum is on this left side here. Okay, and n plus 1 term is a positive value. So what I'm going to do now is I'm going to add to this sum. Okay, I'm going to add to this sum some sort of term, the nth plus 1 term. And of course, if I do that, the new partial sum, including that nth plus 1 term, will be more, right? It'll be bigger. S of n plus 1. Now, we know that the actual sum, and I'll use that as s, is somewhere in between these two dashes. Let me just pretend it's here. This is the actual sum. So if you look at the difference between here, or the difference between the actual sum minus the current partial sum, this would be what we call our error, right? Cool. Now in this case, what is the upper bound of the actual sum? Well, the upper bound of the actual sum should be this. It should be the original sum s of n plus the actual error. Well, what's the largest this error could be? Well, yeah, the largest this error could be is really this distance of the red line, which happens to be a sub n plus 1, or the value of the next term. So that's what we call the upper bound of the sum. Okay, this is the largest the actual sum could be. Okay, well, what's the lower bound? Well, the lower bound would be if that error was pretty much nothing, so s of n. Okay, so that's the case where we have an even n, but what happens if n was odd? Well, in this case, when n is odd, we have the partial sum being pretty large, and then the next term will actually be negative, right, in this alternating series. So now I'm going this way to figure out a sub n plus 1. And of course, if I were to do that, my new partial sum, including that term, would be here, less than the previous partial sum. And similarly, if I had my actual sum, it would be somewhere in the middle. And yes, here's my distance of the error, s minus s sub n. That's my error. And now, if I ask you to look for the upper bound of the actual sum, well, yes, it would just be s sub n, right? The highest term. The lower bound, yes, would just be s sub n minus the error, which in this case, the error, which in this case would be, of course, the 8th n plus 1 term. And similarly, just like this, what we have over here, it's the actual value of the next term. So, why am I showing you all this? Because the diagram above shows that the error, which is the distance between the actual sum and the partial sum, it always must be what? When I compare it to the distance represented by the actual term. That error is always, when I compare it to this, I hope you can say it's always going to be smaller or shorter, right, than the distance. So the distance must be smaller or shorter than the distance represented by the actual next term. That's what this a sub n plus 1 means. So this gives rise to the idea that the alternating series remainder, which is really the error bound, has to be less than or equal to what? The absolute value of the next term, right? I don't care if the next term is positive or negative, but I know the absolute value of that must be a distance that will be larger than the actual possible error. And that's where we get that formula from, where we say the alternate series error is less than or equal to the absolute value of the next term. And the value of the next term happens to be what? Yes, it's the n plus 1 derivative, evaluated at c, x minus c to the power n plus 1 all over n plus 1 factorial. Right? From the Taylor series. So, I hope that gives you a better understanding of these ideas. I'd like us now to go and take a look at the actual 8.1 supplement pages. Okay, I did not create this. A guy named Larry Peterson did, so I have to thank him for that. I went to one of his conferences, and he was kind enough to give us these lovely notes. So I appreciate that very, very much. As we look through here, we're talking about error bounds, okay, and once again we're looking at the alternating series error bound. Yes. And I have this lovely question here, which actually came from the 1995 Calc BC exam. Okay. So remember that when we're dealing with an alternating series error bound, the error is maximized in the next unused term, right? Evaluated at the difference between the center of the interval of convergence and the x-coordinate being evaluated. So, if you look at example number 1, I've got this lovely question. Actually, was on the 1995 Calc BC exam, question number 5. Yes, the real exam questions. So here's a function f of x equals e to the negative 2x squared. I'd like you to write the first 4 non-zero terms and the general term of the Taylor series expansion. So, hopefully you remember this stuff from the previous chapter. Remember what e to the x looked like as a Taylor series? Hopefully remember this nice, easy polynomial. Nice, lovely pattern, remember? Just x to the n over n factorial. So if I were to do e to the negative 2x, notice what I've done now. I've replaced x with negative 2x squared. So wherever I see that in my expression from above, I should replace x with negative 2x squared. Right? Negative 2x squared. I'll try to color code this for you. Squared to the power of 3 over 3 factorial plus dot 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 plus, and then this would be once again negative 2x squared to the power of n over n factorial plus dot dot dot. Cool. And this is a Taylor series expansion about x equals 0, which really is a Maclaurin series. Good. Do you remember anything about the interval of convergence? Well, for e to the x, I hope you remember that the interval from convergence, is really negative infinity to infinity. So it works for all values of x. Okay? So therefore, no big deal with the other ones since I'm not replacing anything with x, so the interval of convergence is also the same. Okay? Now, here's the one I really want you to do. So here it says let g be the function given by the sum of the first four non-zero terms. Okay? Show that f of x minus g of x, the absolute value of that, is less than 0.02. You're like, what? What does that mean? So, what was f of x again? That's the original function. Okay? So think of this like the original function, the original sum. Where g of x is like your partial sum, or the term that you're trying to use to estimate it. So the difference between them, absolute value, well, yeah, that's the error, right? That is the error. And because we know this is an alternating series, and why do we know it's alternating series? Look back up here. Do you see how the terms alternate, right? One of them's negative, one of them's positive, one of them's negative, positive. Then we know we can use the alternating series error. So the alternating series error. And what is the alternating series error equal to? Was less than or equal to the actual next term. So this is the sum of the first four non-zero terms. So I want the actual fifth term then. So I look back up here. Where's the fifth term? 1, 2, 3, 4. Oh, it's the next one here. That would be the fifth term. Well, what's the pattern for the fifth term there? Yes, it's a negative 2x squared to the power of negative 2x squared to the power of, I hope you said 4, all over 4 factorial. Bravo. And now the question I have for you is, what do I replace x with? Okay, I want to make sure this is the maximum error possible. Look at the interval they gave you for x. X has to be between negative 0.6 and 0.6. If it's centered about 0, the largest distance or the radius away would be 0.6. Right, so I will just replace this with 0.6 squared, this whole thing to the power of 4, all over 4 factorial, absolute value of that. And I'll do the calculations, and I'll tell you this is equal to 0.0111974, which of course is less than 0.02. Woo! That is great. So therefore, we have actually shown that f of x minus g of x, the absolute value of that, is less than 0.02. Cool. Okay, so that's really just another way of writing, tell me the alternating series error. Okay, moving on. Here's another one, okay, from the 2010 exam. This time I gave you a piecewise function. Notice how I've even messed you up even more. I've said g of x equals to 1 plus the integral of 0 to x of f of t. Remember doing this stuff from, I think, Unit 6? Definite integrals, putting them together. We're mixing everything up together. This time I said write the first 3 non-zero terms and the general term of the Taylor series for cosine about x equals 0. Once again, that's really Maclaurin. And then use this series to write the first 3 non-zero terms of the general term of f. Okay. So, how can we do this? Well, f of x, my friends. Well, I guess before I do that, what is cosine? It says, what this? Do you remember what the cosine of x is? Do you remember what those terms look like? Remember from last chapter again. Hopefully you remember cosine x. That's what? 1 minus, I think it was x squared over 2 factorial plus x to the power 4 over 4 factorial. Remember that? Dot, 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 dot. Okay. Do you want the general term too? I guess we need that. So do you remember the expression for the general term? Alternating series, so negative 1 to the n. Notice the powers are always even numbers, so x to the power 2n, and divided by 2n, all factorial. Okay? So that's cosine x. So what's f of x then? Well, f of x would be me taking this piecewise function and replacing cosine x with, yeah, what I just had there in green. So let's copy that out. Dot, dot, dot. I wish I had a stamp. Copy, paste. dot, dot. And then don't forget, there's still a minus 1 at the end. All over x squared. And that is true for x not equal to 0. And there's another piece which is negative 1/2. And that is true for x equals to 0. And now what I'd like to do is just simplify this, please. So if I were to simplify this, notice that for the top, the 1 minus 1, that's gone. Good. And now each of these terms has to be divided by x squared. So notice that the first one, the x squared or x squared cancels out, so I'm just left with negative 1 over 2 factorial. And then now it's not x to the power 4, but x squared over 4 factorial. It's minus x4 over 6 factorial. And so for when we do the general expression, notice I took the power of x, which was x to the 2n, and I'm dividing it by x squared. So think about what I'm doing here. Dividing, the bases are the same. How do I divide powers when the bases are the same? We do what with the exponents? I hope you said subtract. And if you did, I'm happy. Plus dot 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 dot, of course, right? This, of course, is true for x not equal to 0, and it's equal to negative 1/2 for x equal to 0. That, my friends, is the answer to part A. Boom. Okay? Now, it says use the Taylor series found in part A to determine whether f has a relative max, relative min, or neither x 0. Whoa. Whoa, whoa, whoa. This is major review stuff. Relative max or min. How do I find that again? Wow. I need, if I want to do that, I need to find what? Yes, I need to find where the derivative equals to 0, right? Well, where is the term? Okay. Actually, not only that, I just want to add at 0, so I guess I have to say, what's f prime of 0? Is that equal to 0? Well, how do I tell? Look at the Taylor series above. Look at the thing in red. Do you have a term that has a first derivative? Remember how the first derivative is related to the power of x, which is the power of 1? So hopefully you can see here that since the f prime of 0 equals 0, and y, I'll say due to the Taylor series not having an x term in it, right? There's an x squared term, so the coefficient in front helps you with the second derivative, right? So the x term would give you the coefficient in front of that. That should be equal to f prime. There isn't one here. So then we know that x equal to 0 is a critical number. So you're right, it can be a relative max or min then. Okay? But how do I know if it's a relative max or min? I can't make a number line here. So the first derivative test doesn't help. Oh, did I give you a hint? Not the first derivative test, but let's look at the second derivative test. That's right. So using the second derivative test, how could I do that? Well, I'll check the coefficient, right? Because that will help me figure out f double prime. And with the second derivative test, if f double prime is bigger than 0, it's concaving up, smiley face, which means it's a minimum. Or if it's negative, it's concaving down, which gives you a maximum. So how do I find the actual second derivative test? Well, I have to check the coefficient where? In front of which term? The x squared term, yes. So where's my x squared term? Right here. So the coefficient in front is 1 over 4 factorial. And remember with the Taylor series polynomial, that represents the second derivative at 0. But don't forget, we're dividing by 2 factorial. So therefore, if I want to actually find the second derivative, I need to multiply both sides by 2 factorial. 2 times 1, 4 times 3 times 2 times 1. I'm left with 1/12. And that, of course, is bigger than 0. So, since the second derivative is bigger than 0, we know this concaves up, and therefore x equal to 0 gives us a relative, what again? That's right, minimum. Wow. Look at all this stuff that is like review. Wow, crazy. Whew. Alright, let's keep going. Wow. Right, the 5th term Taylor polynomial for g. Okay, not for x this time, but for g about x equals 0. Where's g? G just happens to be, oh yes, this. Defined as 1 plus the definite integral from 0 to x of f t dt. Wow. Okay, so how do we deal this then? Well, like the formula says, it's the integral from 0 to x of f of t dt. So where would I get this expression from? Yeah, we've seen this. This is f of t. That's part A. And of course, this is this crazy expression. Here we go, friends. 1 plus the integral from 0 to x. And I'm going to replace the f of x with the expression we calculated earlier. So that's negative 1 over 2 factorial plus no longer x, right? It's f of t. So t squared over 4 factorial. Then minus t to the 4 over 6 factorial, and so on and so forth. Okay, I'm not going to worry about that general term because they didn't ask me for the general term. We're going to do some nice anti-derivatives here. So here we go. Negative 1 over 2 factorial x. Oops, not x. Sorry, my variable's t. Add 1 to the exponent, that'd be t cubed, divided by a new exponent, don't forget the coefficient in front. Add 1 to the exponent, divide by a new exponent, and we're going to evaluate this from 0 to x, so we can now plug in the values. Now it becomes x, negative 1 over 2 factorial x, plus x cubed over 3 times 4 factorial, minus x to the power of 5 times 6 factorial, plus dot, right? And then we'll subtract from that all things with 0, so I love plugging in 0. So now what you'll see is 1 minus 1 over 2 factorial x, plus x cubed over 3 factorial, 3 times 4 factorial, minus x to the power of 5 over 5 times 6 factorial, and that just happens to be the 5th degree, so I'm really thankful about that. I'm going to stop right there. So this is g of x as a 5th degree polynomial. Stop right there. Okay. Now part D says, hey, the Taylor series for g about x equals 0. Hey, that's what we just calculated in part C. Hey, now it's being evaluated at x equal to 1. And I'm telling you it's an alternating series with individual terms that decrease in absolute value to 0. That's great. So can we use that 3rd degree Taylor polynomial about g? Oh, the 3rd degree Taylor polynomial. That means it's just these terms, right? Up to the 3rd degree. To estimate g of 1. Cool. So that's easy then. We can just go ahead and plug in 1 into the first 3 terms. No problem. I can do that. 1 minus a half. Let's see. 4 factorial is 24. Times 3 is 72. So that's what 1 minus 36 over 72 plus 1 over 72. I think that's just 37 over 72. Okay? Now, explain why this estimate differs from the actual value. Ooh. I smell error. Error is less than 1/6, so the error This is an alternating series. Oh, the alternating series error is the absolute value of the next term. Well, what is the next term of this third degree Taylor polynomial? Well, it just so happens to be this. X to the power of 5 over 5 minus x factorial. Negative, of course, right? So it doesn't matter with the negative because we're doing the absolute value anyways, but hey, we'll do that. And since it's centered around 0, but our value is 1, the biggest distance would be the difference between those, so I'm going to place x with 1. 1 to the power of 5 over 5 factorial, 5 times 6 factorial. That, of course, is equal to, I don't know what that equals to. 1 on the top, I know that. But look, I know that the denominator here, 5 times 6 factorial, that denominator, if I compare it with this denominator, yeah, much bigger denominator. So 1 divided by a bigger denominator, of course, becomes a smaller number, so I know this is definitely less than 1 over 6 factorial. And therefore, I've proven so that the error is 1 over 5 times 6 factorial, and it is less than 1 over 6 factorial. So I know the estimate must differ from the actual value, because that's the error, by less than 1 over 6 factorial. Okay? No calculator required. Okay. So that takes care of the alternating series stuff. I thought I'd take the last few moments to show you some Lagrange error. So remember, the Lagrange error is the one where we can use it for Taylor series that don't alternate. Okay? We can still find the error, and the only difference is, yes, it's still tied to the next unused term, but the key difference is it's not just that value of the term. We have to change this derivative expression. This has to be now the maximum value that corresponds to the derivative that it takes on the given interval x, and is the value of the polynomial function centered at a. So the key thing is, when we're looking at this derivative now, we have to look at the maximum value of the derivative in the interval from x to a. That's the only difference. It's not as simple as just using the derivative evaluated at a. So let's go back to 1999, before you guys were born. Here's the Calculus BC exam, question number 4. Notice this one I gave you some derivative values. Okay? And I want you to come up with a third degree Taylor polynomial. So that, I hope, is not too hard. Can you try that yourself? Press pause and then come back and look, please. Third degree Taylor polynomial, T3x, I'll say. Of course, as always, the original value, f of 2, plus, once again, the derivative at 2. And then now, because we are looking at it about x equal to 2, there's the factor x minus 2. Remember, it's the second derivative of 2. Don't forget to divide by the 2 factorial, yes, and then this will be x minus 2 squared. And because I want the third degree Taylor polynomial, welcome to the third derivative at 2, divided by 3 factorial, x minus 2 to the power of 3. That is it. Now, we need to actually plug in these values, please. So, f of 2 from the top, negative 3. F prime of 2, 5. F double prime of 2, 3. So 3 over 2 factorial, or just 3 over 2. And then the third derivative, negative 8, and 3 factorial, 6. So how about just 8 over 6? I'm going to simplify that to negative 4 over 3. Okay, there's your third degree Taylor polynomial. And we're now going to use it to approximate 1.5. So just plug in 1.5. So plugging in 1.5. That's just a half, right? Negative half. Plugging in 1.5, negative half squared minus 4/3, negative half cubed. I will calculate this for you. I got negative 4.958. Okay? If that's what you got, give yourself a pat on the back. Yay! All right. Now it says the fourth derivative of f satisfies this inequality. So the fourth derivative of f is always less than or equal to 3 for all x in the closed interval from 1.5 to 2. How convenient, right? Since I'm evaluating the point at 1.5 and it's centered at 2. So use the Lagrange error bound on the approximation to f of 1.5 to explain why that value f of 1.5 cannot be actually equal to negative 5. Oh. So really what I'm saying is, look, our approximation is pretty close to negative 5. But because of this statement here, I'm supposed to calculate the error. And the error is going to dictate that I know its actual value, the real value, cannot be negative 5. Well, let's just calculate this this error first, right? So this Lagrange error, okay, Lagrange error. How do we calculate this again? It's less than or equal to the absolute value of, yeah. Now it's the next term, right? The derivative of the next term, evaluated at z, right? Once again, this is like the maximum, right? The max value. Then we're going to multiply by x minus a to the power of the next term, divided by n plus 1 factorial. And in this case, the next term is what? Because the previous question said this is a Taylor polynomial of degree 3. The next term must be degree 4. So f of 4 of z. X minus 2 to the power of 4 all over 4 factorial. Good. Now here's the big question. What is this going to be? Or what is the largest this could be in the interval? You got it. 3. So we're going to replace that with 3. And our x value is 1.5. So I'm going to replace x with 1.5. And you just need to calculate this expression now. And when you do this on your calculator, you get the number 0.007812. Now, okay, fine and dandy, but still, how do I use that to explain how this cannot be equal to negative 5? Well, if I want to look at my lower bound, because this is the maximum error, right? If I were to take out the lower bound of my possible actual values, I'm going to take my answer from above, which was negative 4.958, and I'm going to subtract the actual error, 0.07812. This is the maximum error. So if I subtract that, what you'll see is this becomes, oh, by the way, why would I not add this? Yeah, because if I add it, it's smaller. I definitely won't get close to negative 5. If I subtract it now, yeah, I get negative 4.966. And notice this is still bigger than negative 5. And since that's the maximum error, right, this is the maximum the error could be, therefore I know that the actual value of 1.5 now can never equal negative 5. Okay? The largest or the lowest it could be would be negative 4.966. Okay. So part C, write the fourth degree Taylor polynomial for this lovely expression, and then use it to explain why G must have a relative min at 0. Oh, we've done that kind of stuff before, right? So let's do the first part. I'm going to have to come up with a fourth degree Taylor polynomial for G. Well, what I do know right now is I have this thing, right? Then I do f of x up here, right? Write a third degree Taylor polynomial for f of x. So I'm going to use that. So I'm going to use probably this expression here. Okay. Copy paste down here, please. So I'll say t of x equals to negative 3 plus 5 bracket x minus 2 plus 3 over 2x minus 2 squared minus 4 thirds x minus 2 cubed. And now if I want to figure out f of x squared plus 2, because that's what g of x is now, I better replace this with X squared plus 2. Okay, and I want, what, the fourth degree, so I'm going to stop at power 4. So here we go. This becomes now x squared plus 2 minus 2. This becomes 3 over 2, x squared plus 2 minus 2 squared. Oh, I see I don't even need this term. Do you know why? Let's simplify. Do you see this? X to the power of 4. If I did one more, it'd be more than x to the power of 4. Don't waste your time. Cool. So there is my function for g. Okay? This is g of x. Actually, I shouldn't call this g of x. I should call this p of x. G of x is the actual thing, right? P of x is the polynomial that represents g of x. So, use this to explain why g must have a relative minimum at x equals 0. So, relative min means I'm looking at the derivative, right? So, let's look at g prime of 0. Notice that there is no term here, right? So, g prime of 0 equals 0. Why? Since there is no x terms, just like one of the questions we did earlier in this video, right? And then now, how do we tell it's the relative minimum? Once again, we look at the coefficient of the x squared term, because using the second derivative test, I know that g of 0 over 2 factorial must equal to number 5. Therefore, g double prime of 0 equals to 10. Therefore, this is concaving which way again? Up, which means therefore this is a relative minimum by the second derivative test. Nice, 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 nice. Okay. There are two more questions here that I want to try. I know this is a super long video. I apologize, but you know what? Let's finish off and do this well. Or maybe if you want, just pause right now, take a break, then come back. Or even pause, do it yourself, and then come back. I'm very happy about that. Okay? Lots of interesting data in this little chart. Got a function h. Selected values are there. The function h and these first four derivatives are increasing on the interval from 1 to 3. Okay? So, it says write the first degree Taylor polynomial for h about x equals to 2. So I'm thinking, look at this line of stuff and use it to approximate 1.9. Okay, so first degree Taylor polynomial. Thank goodness. Whew, I can do that. That's pretty much like a line, right? First degree. So that would be the original value, h of 2, plus the derivative, h prime of 2, x minus 2. Yeah, you're thinking, doesn't this look like the equation of the tangent line? Yeah, or a tangent line approximation. You bet the tangent line approximation is really the first degree Taylor polynomial approximation. Same thing. Here's 80, 128, and x minus 2, right? Those are the values that I need. So, approximating 1.9 now, so I guess this is the same thing as h of 1.9, right, to approximate. So, I will actually just plug in 1.9, 80 plus 128 times 1.9 minus 2, that's 0.1, that's 80 plus, or 80 minus actually 12.8, and that's 67.2. Cool. Okay, there's my approximation. Now here's the next part. Is the approximation greater or less than the actual value? Oh, how do I know that? I have no clue what the actual value could be. Remember those questions before when I said, is it an overestimate or an underestimate? Tangent line approximation questions, remember those? Remember, you draw the tangent line, and then if it was concaving up, oh yeah, that would be a underestimate. If it was concaving down, oh, it'd be an overestimate. Same thing here. Did you hear me say the word concavity? Where should I be looking for concavity? Yes, I need the second derivative. And in this case, it's 488 over 3, which of course is bigger than 0, which of course you have now know is concaving up, which means of course the approximation is an overestimate or underestimate, or actually greater than or less than. So the approximation is of course less than the actual value. Right? That's this case. The actual value up here, my estimated value down there. Okay, that's part A. Part B, write a third degree Taylor polynomial now and use it to approximate 1.9, so not too much harder. I'm just going to extend it. Right? Third degree Taylor polynomial. That's just h of 2 plus h prime of 2. Notice the pattern, h double prime of 2 over 2 factorial. Many people forget that factorial stuff. H triple prime over 2 over 3 factorial. Yeah, and then you just have to plug things in. So we already had that first part, 80, 128. I'm going to skip a step and actually plug in 1.9 right away. What was this double prime? That was 488, I think, over 3. Don't forget the 2 factorial, 1.9 minus 2 all squared. Triple prime, what was that? 488 over 3 times 3 factorial. And you just have to calculate this, and I'll do it for you. I got 68.005. Okay. Alright, and finally, use the Lagrange Error bound to show that the third degree Taylor polynomial at x equals 2 that approximate this value h of 1.9 has an error less than, this small number, 3 times 10 to the power negative 4. So they tell you what to do, Lagrange error, right? What is that again? The next term, right? F of nth plus 1 evaluated at z, because it's the maximum value, x minus a to the nth plus 1 term, n plus 1 factorial. And in this case, because it used to be the third term, or that's where it stopped, the next term, of course, is the fourth term. So I want the fourth derivative at z, x minus 2 to the power of 4, all over 4 factorial. So once again, what do we replace this with? Haha, they gave it to you, the fourth derivative. Okay. We don't know if this is the max or not, but it's the best guess that we have. Okay. I guess you can compare, right? What is 584 over 9? 584 over 9. Wow, that's 64 something, so that's much bigger than the 18, right? Yep, so, yeah, we'll just use that. Okay, so let's plug that in. 584 over 9, 1.9 minus 2 to the power of 4, all over 4 factorial. Going to do this calculation for you. I got 0.00027, and that definitely is less than 3 times 10 to the negative 4, because that's 3 moving 1, 2, 3, 4, so that's 0.0003. It is less. And there you go. You've proven that there too. Alright. Okay, your brain is probably fried by now, but that's okay. We're going to do one last example. This one, I'm not going to do it all because part of it we actually did before already. You hopefully remember doing this from the, I think, 7.6 extra handout. Yeah, I think you would have done it there. If not, you can do it yourself. But I'm just really curious about the last one. And maybe I don't even need to do this because we've done so many examples of Lagrange error already. But if you look at this, I'm asking you to show that the error between the polynomial and the actual value is less than 1 over 3,000. Once again, because this is not an alternating series, we have to use the Lagrange error bound, which would be the next term. This is the power, or the 4th degree polynomial. I then should be looking for the 5th. It's centered about 0, so x minus 0 to the power of 5 all over 5 factorial. And thankfully, friends, this is equal to there. Perfect. Now, notice I'm asking you to go from 1/4 to there, so if I actually went from 1/4, here's 1, I'm actually looking at this region here, so the maximum value just happens to be right there, a little bit less than 40. Okay? So the key thing here is to estimate what that could be. I'm thinking, well, that's 20, let's just say that's about 30. So that maximum value here is 30. Okay? And then we know that the corresponding x value is 1/4, so we can just plug in 1/4. And I hope you can do the calculations here. 1/4 to the power of 5, I guess that's a big number, but 30 over 5 factorial, 30 over 5 factorial, that's 120. Oh, that's actually 1/4. So it's 1/4 times 1/4 to the power of 5. That's just 1/4 to the power of 6. 4 times 4, 16, 256. I think it's 1 over 4096. So what do we know about 1 over 4096? That is definitely less than 1 over 3000. So since 1 over 4096 is less than 1 over 3000, we have shown that the error, right, the error then is less than 1 over 3000. Drop the pen. I'm done. And so are you.